And hopefully I won't be giving next week's seminar as well. We may escape home soon. So okay, I'll present, so the work that both Trevor and I presented last week, for those of you that were here, was aimed at using generative models and learning generative models for parsing and translation. This will be a different look at how you can integrate ideas from machine learning into machine translation. In this talk, I'll talk about conditional models and discriminative models and some work that we did a few years ago applying these models to translation. So I have some introduction slides here, but that will be in some ways going over ground that I'm sure you're familiar with. So I'll probably move quite quickly through the introduction. And there's two main bits of work that I'll talk about today, using conditional random fields to do word alignment, discovering translation correspondences in parallel sentences, and the second piece on using conditional random fields to train synchronous grammar-based models. And then I'll finish with some comments about where you might go with this in the future. So some quick history. So we're all familiar with machine translation. The general aim, we want to be able to take foreign texts and translate them into a language which is useful. This is very difficult. It requires, to do it completely, it requires AI hard reasoning. We can't really do that. So in statistical machine translation, we take a very shallow surface-based approach and hope that we can do well enough. And often we can. So a lot of the origin of the statistical approach or in machine translation in general, you can trace back to the influential memorandum of Warren Weaver shortly after the war. And here's a quote where he, in some ways, foresaw the use of statistical methods in machine translation. Of course, it was another 40 or 50 years before people actually successfully used such methods successfully. And the whole reason why we can do statistical machine translation is because we can get hold of Parallelcorpora. And in some ways, this is the coolest thing about machine translation, is that we don't have to pay for our data. It tends to come about for free. We can Parallelcorpora for many popular languages are relatively easy to come across, from the Europal proceedings, the UN data, and this goes way back to things like the Rosetta Stone in history. People naturally produce Parallelcorpora, and we can use it to build translation systems. And that's one of the great things about machine translation. It's very light. There's a very light reliance on producing the corpora. So yeah, people produce this in all sorts of ways, from translating ancient texts to the modern example where we can, where there's sort of, in some ways, limitless web resources for gathering Parallelcorpora, like the UN websites. So when we focus on this problem of machine translation, fundamentally in some ways you can think of it like a classification problem, that we have an input, which is our foreign sentence, and we need to produce the output sentence. Of course, you can't really treat this directly like classification because there's too many output sentences. You wouldn't want to have a different classifier for each possible output sentence. So we need to break this process down. Essentially, there's some sort of latent process going on where this arrow is. We're not really sure what it is, and that's what we need to model. And much of the work in machine translation has been trying to come up with different ways of representing this latent process. Different models which balance in some way tractability with representative expressiveness. And so, of course, the early models, the IBM models, were word-based. They aimed for a sort of tractable representation. There was a strong emphasis on learnability, coming up with a representation that we could learn while being linguistically sort of completely inadequate, but still possibly effective. So this is a representation of IBM Model 3. The word-based model here represented as a series of transduction steps. In the first step, we replicate words in order to support words which have multiple, a single word that translates as multiple target words. We translate words. We can insert words that weren't in the source, and we can remove words that were in the source. At some point, we have a lexical transfer step, and that's where we do the translation. The interesting thing about these models to note is that here where we have zoom translators as the and to, these transfer steps are done independently. There's separate parameters, which is very inadequate from a modeling perspective. But there was a choice that was made to make things tractable. And finally, the final step here, the distortion step, where we change the order of the words. In some ways, this is the key step, and it's occupied a lot of people's researchers coming up with good ways of doing this, because this is very much the difficult part of machine translation. If we didn't have reordering, things would be far easier. If we didn't have reordering, we'd all be doing speech processing. And this is what makes machine translation different from speech recognition, and it's what makes it difficult. So that was one of the early models. Of course, we don't really use that for translation anymore. We've moved on to other representations. But we still do use it often to produce word alignments, to produce correspondence lattices that look like this, where we mark which foreign words are aligned to the, in this case, the English words here on the right by the squares. So we can use those word-based models to produce these alignments, and then we can use these alignments to learn more complicated models. And currently the sort of popular and state-of-the-art way of doing machine translation is this sort of approach of phrase-based translation, where we in some way segment the source sentence. We translate the chunks of source sentence into target sentence chunks and then reorder them, and use some sort of generally linear distance-based reordering metric to learn the reordering. And this is probably the most popular and I would argue the most successful currently way of doing statistical machine translation. And people like Google use it. So if you type a sentence into Google to get it to translate, it will be doing that sort of phrase-based translation on the previous slide. Very, very shallow, very linguistically impoverished, but also quite fast, easy to scale in the sense that Google needs to scale things to lots of data, and moderately effective. But sometimes this sort of approach doesn't work, and here's some brief examples from Arabic and Chinese to illustrate this point. And this is illustrating when you have, some languages are closer to each other than others. If we look at the Arabic, the way some of these strings are expressed in the English and the Arabic is quite similar, particularly the word order is similar. You can see from this example here and this example here that so these in the brackets are the gloss of the Arabic, and up the top is how we'd say it in English. So the word order from the Arabic to the English is relatively linear, whereas the Chinese is not. The Chinese is entirely different, and even the semantics of the lexemes is quite different. So the transfer from Chinese to English is just going to be far more difficult and far less likely to work with these sort of surface phrase-based type models. So that's why we have lots of challenges still in machine translation, working at how we can deal with this effectively. Okay, so there's a fast and brief introduction. I'll move on to word alignment and using conditional models for word alignment. So those of you that work with machine translation know that we generally start with a large parallel corpus and then run some sort of generative word alignment model over that corpus. The most popular one is called Giza++, and that gives us lattices like this that we can then learn our translation models from. In this section of the talk, I'll talk about, instead of using these generative models, can we use a conditional model? And this means that we're talking about supervised learning of alignment. So we need some hand-annotated word alignments, and from those we're going to learn this process. And the reason we'd want to do this is because discriminative models allow us a great deal more freedom with how we represent the alignment. We can use much more interesting features than just these two words co-occur frequently. So we can look at morphology, we can look at a great deal more. We can look at the syntax of the two sentences and use all of this to inform the alignment. So there's a great deal more scope to do more linguistically interesting or more articulated models of translation and correspondence. So yes, as I was saying, at the top there, the most popular way of doing this is this Giza++ toolkit that implements the IBM models. Discriminative models, they allow us more powerful features. previous people, there's been a number of discriminative models. Often the models proposed used intractable search spaces, and the particular model I'll present here using a conditional random field, a nice property of it is that we can do exact inference within that model. But one caveat at the bottom is that we require annotated alignments in order to do this. So yeah, there's a trade-off here. So the Giza models allow us to do alignment without any supervision, without having to annotate anything, but restrict us quite severely in what sort of expressive features we can use. Discriminative models allow us a great deal more freedom at the price of having to annotate data. So at the top here, I've got the equation for the conditional random field that I'm using. Many of you probably aren't familiar with conditional random fields, so it may look a bit cryptic. I'll give a brief explanation, but don't worry too much if you don't understand the actual equation. But the idea is that we have an alignment A, which is just a correspondence between the two sentences. We have an E for English sentence, if you like, and an F for foreign. It's very English-centric, but it's the standard way of referring to things. So we're saying that we're going to condition on these two sentences, we're going to produce A. So it's sort of like, you can think of this like a structured learning problem. So in pos tagging, we condition on a sentence and we produce a sequence of pos tags. Here we're conditioning on two sentences and producing a sequence of alignment indices. This is a standard equation for a log linear model. On the top, we have an exponentiated sum of features. So h is a feature function, and this is just all the parameters that the feature function takes. Each feature function has a weight, and we sum all those up, and we divide by the normalizer z. And z's just the sum of the feature weights for all possible alignments. So this is essentially a standard log linear model equation. And the main things to note are what goes in here in the feature function. So t is our what is t? T is our current index that we're aligning. At minus 1 is our previous alignment index, what we align the previous word to, what we're aligning the current word to, at, and these are our two sentences. So it means we can have features which take information from anything which is anything related to these two sentences, because these are conditioning context. So we can have parse a sentence, we can look at properties of the parse trees, we can look at morphological analyses of the two words we're trying to align. We can do anything like that and use those as features in this model. The one thing we can't do is have long distance reliances between alignment points. We can only look at neighboring alignment points in the features. And all this adds up to, so this is a standard complexity for a conditional random field, L being the label set squared, which is the dominating factor, times the length of the sentence. That gives you the general complexity of a CRF. Because our label set here is the indices of the target sentence, we get that becomes T, and so this is the complexity of doing the alignment. So we have a cubic term there. But this is quite manageable and perfectly fast on all the data we'd like to work with. So here's a diagrammatic representation of this model and what it's doing. In alignment, word-based alignment, we tend to run our models in two directions because they're directional models. So we run them switching the source and target, and then we combine the outputs. So I've shown here on the top one direction and on the bottom the other direction. If we just look at the top for a moment, you can see that what's happening is that we're stepping through the source sentence. Here it's French. For each French token, we're predicting an index. And that index says which word in the target that word is aligned to. So you can think of this very much like something like pos tagging, part-of-speech tagging, but instead of part-of-speech tags, we're assigning integers, and the integers imply an alignment. And then we can do the same thing in the other direction. You'll notice that there's some limits on what we can manage. So we can't align the French here to spend, because we can only choose one alignment index. If we go in the other direction, we can align to and spend independently to the same French token. So the directionality in some way limits whether we can do one-to-many or many-to-one alignments. That's why we do it in both directions and combine them. the main thing to note here, and the main thing that makes this different to, say, something like part-of-speech tagging, is that these labels here carry no information in themselves beyond an index. So we don't really want to learn a model that just predicts, that has different features for each index, because of course words appearing in different indices still should align. The index is not what we're interested in, it's the alignment that we're interested in. So all our features ignore the index per se and just a condition on what the actual alignment is. So that's the key difference between building one of these models for something like POS tagging or named entity recognition and building one for alignment. You have this different generalization of the features. Okay, so I'll present some experiments that I did with this model. All these were done on the Canadian Hansard's corpus, where we had some hand-annotated word alignments to train on. The training data for this is very small. We're talking about, in total we have 484 annotated sentences, a very small number of sentences. And we split that up in this way we're only actually training on 100 sentences. We use the 37 development to tune some parameters, and we test on the 347 sentences. So in order to get a model, obviously in those 100 sentences, there's going to be very few lexical alignments that we'll actually observe. So we can't hope to learn actual lexical correspondence. So we're going to have to get that from a larger corpus. So we also have 1 million or so sentence-aligned, a parallel corpus sentence-aligned, and we can use that to take statistics, which we can then use to define our features for the 100 sentences. So that's what we do. We take lots of statistics and we use things, one thing called the dice coefficient. Some of you are familiar with that. It's essentially a co-occurrence statistic between words and the source and the target. We can also train simple IBM models like IBM Model 1 and use the probabilities from that as features in our discriminative model. Or we can go further and train all of the Giza models and use those as features in the alignment. And I'll also present some translation results when we then use these alignments to build translation models and see if they help help us to build better translation models. So we used a great number of features in these models and tried out quite a few different ones, and I'm going to gloss over all of those in this talk to keep it a bit briefer and just focus on one type of feature. So we had lots of other features which looked at words, word matches, and some simple morphology and such. But I'm only going to talk about one type of feature we used, which is the Markov features. And this is because it's a very powerful type of feature. So this is a feature which looks at the previous alignment that we chose and the current alignment we're proposing to choose, and conditions on those two. So we can learn a weight over the relationship between alignments. And if you think about this, what happens is, particularly if we're working with something like French and English, the alignments tend to follow a diagonal in our alignment matrices because the languages are quite similar in word order. So the model can learn a strong preference for following that diagonal. And I represent that here. So we have a feature. So if this is our previous alignment point, this is our proposed alignment point. If we follow the diagonal, our feature is 0. That's in some sense, we can think of that as the default. And then we measure the offset from the diagonal with another feature. So here the offset is 1, 2, 3, 4, and same in this direction. And that gives us a feature which can penalize deviations from the diagonal. This is, in a rough sense, equivalent to some of the Markov features used in, for instance, the Giza Hidden Markov Model, although there's a slight difference in the way they're set up here. The advantage of these models is we can try quite a few of features based on this sort of idea. And these results here we have a base model which uses no Markov features, and it gets a certain so this is an F-score, alignment F-score. So if we add a feature which is the absolute label difference, which essentially is this feature I've described here, we get a big increase in performance. So these features really make a difference. So what's essentially happening is that the model can use these features to guess alignment points. Where there's very little evidence for an alignment, you can guess, because the alignment follows a diagonal, that it may well be a good alignment. We can just have a feature which says is the difference positive or negative. So we can learn a preference for going forward or backwards at certain points in our alignment. And that also gets us pretty much the same improvement. These are trying these features individually. So adding the features individually to this base features. Something I haven't talked about, which is a complication here, is that we have null alignment. So sometimes we align a word to nothing. And that sort of messes up our Markov order. So we can also have a feature that says whether we're coming from or to a null alignment. And that has a little effect. What's that last feature? Forward, backward. What was that last feature? So essentially we can also separate these features rather than taking the absolute, this is an absolute feature, we can separate those out, and that doesn't work quite as well. Okay. There's about 350 test sentences, and normally the average is about 30 words. I don't know exactly what it is for the test sentence, but so there's quite a few alignment points. Yeah. So here's a sort of graphical representation of the same ideas. The way to read this, don't worry too much about this this key here. The square points with the asterisk in them are what the model predicts without any Markov features. The round points with the cross in them are what the model predicts, the additional points the model predicts once you add these Markov features. So without the Markov features, we predict this point, and this point. And you can see that they're for instance, we get the determiners, and we get petrol, oil there, and the full stop at the end. Things that are relatively frequent and easy to predict. Once we add the Markov features, the model learns to fill in the gaps, essentially, because it knows that these essentially follow a diagonal. So where it has some evidence for an alignment, but not enough to commit to an alignment, the Markov feature gives it that bit more evidence to say that it probably is an alignment. So these features, so what I'm trying to argue here with these couple of slides is that these features make a huge difference. Whether whether we'd see the same sort of results for aligning Chinese, for instance, probably not. Because there, of course, there's far less of a Markov monotone relationship between the two languages. But for European languages, when they are quite close in word order, this sort of modeling power is very important. If you want to get good results with an alignment model, you need some way of representing this bias. So if we look at how this all works, when we look at some final results, on the top here is, so we have the different directions. We can go from French to English or English to French, or we can go both directions symmetrized, which is where we get our best overall F score here. This is using a standard set of features which don't use the Giza IBM model. We can do the same, but use the existing IBM model for alignments as features in our model. And then we do slightly better. And finally, we can compare this with the Giza model itself, the standard system, and we see that we're doing better in terms of F-score. But F-score is not the whole story. So some interesting thing to look at this table is that Giza does much better on recall and much poorer precision, whereas the models I'm building have much higher precision, and sometimes quite high precision. Like this is 98% precision on the alignment points, which is pretty good, but the recall is lower than what Giza's giving. So there's this question for, if we build translation models, do we want high precision alignments or do we want high recall alignments? So if we look at some end-to-end translation results, this top one here is a model built using this alignment. And we see that its blue score, so blue, this n-gram-based measure of translation quality, is slightly better, so bigger numbers are better in blue. So we get a slight improvement by using this discriminative alignment for French. If we look at the breakdown of the n-grams in the blue score, we see that this improvement is coming at the higher order n-grams, the bigrams and trigrams, whereas the Giza model is getting more at the unigram level. And we can relate this back to these numbers. So what we can say is that Giza's producing a lot more alignment points. It's got much higher recall. So although we're getting a lot of noise, we're also getting more translation units themselves. So we're going to have less out of vocabulary source terms, and we have more chance of picking up rare translations, and therefore we might see a higher unigram count. But once we start sticking these together into bigger and bigger translation units, the low precision starts to hurt us. This is one hypothesis, that as we build bigrams and trigrams and quadgrams out of low precision alignments, we start to get too much noise and not enough actual quality. I do, but I can't remember them. I can give them to you later. But I can tell you that this system extracts a lot more phrases because of the discriminative, because it has less alignment points. So it's a bit of a technical detail of the way phrase-based systems extract phrases. If there's unaligned words, they extract lots more phrases. They extract every possible combination. As this one has higher precision, there's a lot less alignment points, whereas the Giza one has lots of alignment points spread all over the place. Okay, so that's basically the results of using these models. So we can definitely get more precise alignments, and we can make some improvements to translation quality. Where you'd take this further is looking at more interesting languages. And for instance, Czech would be a great language to do this with, because one, you have a lot of alignments, I believe. So you've got the data annotated. Two, there's a lot more interesting things going on than French and English in terms of morphology and correspondence. So there's a great deal that you can extract features on. Things like case and gender and such. So I think that's where these models are going to have more of an impact. And other languages where for instance, where the reordering might be bigger, but in some way informed by syntax. Because of course, something I haven't done here, but you can do, is add syntax trees and have features which say, am I moving the prepositional phrase over the noun phrase or something like that, which could be very useful for languages like Chinese or something like that. Okay, so I'll move on to the second part of the talk. So I've talked about that first stage in building translation models, the word alignment, where the actual translation units come from. The second part of any translation model is the actual decoding, how we take those and we produce an output translation. So can we take these ideas of discriminative learning and apply them there as well? So again, I come back to my little picture here with the two sentences and the question mark in the middle saying, we don't really know what's going on here in our translation process. So in this model, I'm going to introduce this idea of a latent variable. So we're going to say that there's lots of different ways you can get from that input to the output sentence. And we're going to do some sort of probabilistic summing over all these possible ways. So first problem we have to deal with when we think of doing discriminative learning for actually producing a translation is that we don't have a gold standard derivation, in the sense that we don't have a single way of going from that source to the input to the output, which we can optimize essentially. Normally in discriminative learning we have some sort of gold that we optimize towards against all other possible options. In translation it's more difficult because we know what the output sentence should look like, or we know one example of an output sentence that is good. There may be many other translations, but we don't know how we got there. So there's many ways of getting to that output. And so we need some way of incorporating that into our model. Secondly, Parallelcorpora are very noisy. So often the sentences that we're training on aren't particularly literal translations of each other. There's all sorts of other noise in there, dropped semantic information and such. So any model we propose has to be robust. And finally, whenever we do these discriminative models, they tend to be resource intensive. They tend to be heavy, take a lot of computational resources. So any model we propose must be able to be trained on a significant amount of data if we're going to learn interesting translation features. It's no good proposing translation models that only train on very small numbers of sentences, because we'll never get state-of-the-art performance. And that's something we're still struggling with, to be honest. Okay, so this question of derivational ambiguity and not knowing exactly how to produce a sentence, I represent here with a small example of a slightly non-literal translation between English and French, where we've dropped the adjective. So if we think about in a phrase-based system how we would break this up into phrases to produce this translation, any of these examples could be used to in a phrase-based translation system to produce this. So we could break the sentence up on the determiner and the adjective. We could translate it as one full unit like this, and we're not sure which one of those is the correct one to do, because we're not told. We don't observe that. We just observe the input and the output. Now what we can do is train a maximum likelihood model to say which one we should choose, and it will always say this one. So maximum likelihood solution is always to take the biggest translation unit you can. And if you do that on whole sentences, you'll learn to translate whole sentences as whole sentences. So one of the first problems we need to tackle in building conditional discriminative models for translation is regularization. We need some way of biasing a model away from the maximum likelihood solution, because we know that that's bad. We don't want to learn to translate whole sentences as whole sentences. So the aim of this work, we aim to build a translation model based just on binary features. So we didn't want to use any features extracted from existing translation models to see how such a model would work. We want to do this on a significant amount of data. Previous discriminative models are all based around hundreds of sentences. We want to do at least tens of thousands. We want to do it with a model that we know works. So we don't want to have to change the model to fit our learning algorithm. So we do it with the high-row translation model, which we know can give state-of-the-art performance. And one of the hardest parts of doing this is to incorporate a language model. Because without a language model, we can do all the inference in these models tractably. As soon as we add the language model, nothing's tractable anymore. So a quick review of synchronous context-free grammar. So in synchronous context-free grammar, what we do is through a CFG process, we produce two sentences, a source and a target, simultaneously. On the top box here, I have an example of a synchronous context-free grammar. So it looks just like a context-free grammar, except that on the right we have two sets of symbols rather than one set of symbols. And so what we're saying is that here, S being our goal symbol, rewrites as an X on the source and an X on the target, where X is a variable. The indices on the variables imply an ordering or a reordering. So here we have an X produces two X's, and because the indexes 1 and 2 are in the same order, then those constituents are in the same order. Here we're encoding a reverse. So here we're saying that we can reverse constituents. So on the bottom, if we step through a process of deriving a source and a target sentence using this, so the first thing we can do is start with the goal symbol, and so I highlight on the top the rule that's being used. The first thing we do is produce a goal symbol. It produces two child X constituents, one in the source and one in the target. Using this rule in the top here, we can replicate each one of those X's to produce two new variables. So this is a standard sort of way of generating a sentence with a CFG, but we're just doing it in 2 dimensions rather than 1. Here we can replace one of those variables with a lexical translation. We can again replicate the other variable. Again, we can introduce a lexical translation. We can use phrasal translations if we want. So here, will to wants to. We can use this rule for replicating the variables, which now reorders, so reverses the order of the variables. So you see that the 6, 7 here becomes 7, 6. So we swap their order. Now we replace that x6 variable again with a lexical translation, a phrasal unit here. And now you can see that variable x7 that's left hanging around is now in a completely different place in the two sentences. So this is where we're getting reordering from in our synchronous our SCFG model. And you can see that in this case what we've done is we've got this nice example of modeling the verb final construction in German. So we can show that the verb's moved from the end of the sentence to in between the subject and object. And finally we can fill that verb in and finish the derivation. So synchronous context-free grammar is just a nice formalism for describing the generation of parallel sentences, and very popular now in translation. Okay, so now we come to the discriminative model. Again, we're going to see equations, these conditional log linear model equations, very similar to the ones I used in alignment. just with some slight details in the model we're applying them to here. So again, we see we have this probability here. We have D, which is a derivation. So that's one way of getting from our source sentence to our target sentence, or one parse tree in our synchronous context-free grammar. And the sentence it produces, which is E, so that's the target sentence. So the probability of the derivation and the target sentence given F, the foreign sentence. So in some sense, you can relate this to the alignment model, except that now E is no longer conditioning. Now it's being generated. Now it's on the. Now it's what we're learning. So again, on the top, we have an exponentiated sum of feature functions. So here we have a big H, and our feature functions are defined over the derivation, the source, and the target sentence, or target and source. Sorry. And we have weights for each feature. And again, we have Z, our normalizer. This time, Z's a bit more difficult, but because we've set things up in a nice context-free grammar formalism, we can actually calculate the sum over all features of all possible translations. But a second step is to say, well, we don't actually want to predict a derivation. What we want to predict is a sentence. All we care about is a translation. We don't care about the tree. We're not interested in producing syntax trees. We just want to produce a good translation string. So we say that, well, the probability of E is the marginalized, so we marginalize out the derivation D by summing over all derivations. So we're going to say we want the string which has the highest probability when we sum over all its derivations. Now, we can actually do this in training. We can actually train a model to optimize this conditional probability here, which is quite, from an algorithmic point of view, that's quite cool. That there's a tractable way of doing this with a dynamic program. We can't do it in decoding. So we can't get the highest probability string once we've trained our model, unless we can't do it exactly, so we'd have to resort to some sort of approximation. But the most interesting thing to note is that in training we can do this. So we don't have to make a choice about what our gold standard derivation is. We don't need a corpus marked with one derivation. We can sum over all the different derivations. Andres.
This summing after derivations is very different to what is being done in state-of-the-art decoders. I have another question, that is, what's the key difference between the conditional random fields, like the first equation you have there, and the thing that is being called log-linear model?
Conditional random fields is a sort of slightly difficult term because it was used for a particular model that someone proposed in a paper, and it was deriven from Markov random fields, just being the conditional form of a Markov random field. One way to think of it is a conditional random field is a log-linear model. Not all log-linear models are conditional random fields. So if you're saying how does this relate to what people do in machine translation at the moment, in that sense, this model is structured. So we're doing inference over all the possible trees, whereas in a current translation models, you just have, for a given translation, you have 10 features. So it's not, well, in some sense it is structured as well, but okay. The main difference, there's two main differences. One is simply the number of features we're using. So rather than 10, we're going to be using 10 million. The second one is that we're actually going to normalize. So what people currently do in translation is they call it a log-linear model, but they never actually calculate the probability because they can't. But we structured this model so that we can. So we can normalize, we can do the sum over all possible ones. So we can calculate Z, and that changes how the things we can do in training, which is why we can use 10 million features. So because we can calculate Z, we can use huge numbers of features. We can use, basically because we can use convex gradient-based optimization techniques. Whereas if you're familiar with current approaches to translation, they use first order, essentially heuristic search, MERT, which can't cope with very large numbers of features. Okay, so these feature functions, again, we have this question of what can we do with these features, because that's in some ways the most interesting point. So we, as I've been saying, we decompose this capital H features over a particular translation into features over each step in our derivation. So think of those as the CFG rules. So our features decompose with the rules in the derivation. And the sorts of features we can have, anything on the rule that we're applying, so we can look at features of the reordering, anything that looks at the source sentence. So the source sentence is fixed. We're not producing that in this model. So we can have any feature over any part of the source sentence. So if you imagine we have a parse tree on our source sentence and we're translating a particular word, we can look at the other words that word should agree with on the source side. On the target side, we're limited to just the context of the rule we're producing. So this is quite powerful. This allows a lot of things to be used as features. And the final complication here is a little function here represented as Q. And this is a complication that comes about from the language model. So we're also doing this with a language model. So for each rule in our derivation, we're going to decorate it with the lexical context that it produces on the target side. So if we have a bigram language model, for each constituent we're producing on the target side, that context will be the left word and the right word of that constituent on the target side. And that allows us to calculate the language model probability. But it also allows us to have other features over those words. So we could have a discriminative language model which had gapping and or looked at morphology or part of speech tags as well. So that function Q, what it does is it gives us, for a given rule and a given derivation, it gives us the target side language model context. Yes, and I had this slide here to demonstrate what that was. So if we have this parallel German-English translation here, these indices here represent our indices in our chart cell. This here is a hypergraph. Probably not something many of you come across, but quite common now to think of translation in terms of hypergraphs. And each cell here represents a state in the parse chart. So you can see that we can start by translating span 1 to 2 here, and Q, that context function, will just have the English everything. So we're going from the German to the English here. And for the other words, we do the same. So each span, and we record its. So here, of course, the left and right of this constituent is the same thing because it only spans one word. When we get up here, we combine these two, so we combine 1 and 2 and 2 and 3 spans. So we're just doing parsing here into a span from 1 to 3, and here's its language model context, everything and. When we get to the final constituent here, it's the only place where it actually sort of gets interesting with this Q function. Here we don't need to include what's in the middle. We can just recording the left and right boundary words, so the everything and the anything, which comes from span 3 to 4 there. So this is just to try and give you some intuition about what Q is. Q is just the language model context. So this language model context causes lots of problems. Because if you think about parsing and decorating each parse chart cell with these lexical boundary words, it's going to blow up the search space in the parser. So we need some way of dealing with that explosion in search space. We're no longer going to be able to do exact algorithms like Viterbi, the inside-outside algorithm, because they're just too computationally heavy. And for the high-row model we're talking about, we're going from, without the language model, it's a nice n-cubed order complexity. With our language model, with a trigram language model, it becomes n to the 11. So still polynomial, but not terribly practical. So we're going to need to approximate in some way. And the approximation is required because what we're interested in is calculating this z, this sum over all derivations. So we can't do that tractally anymore. So we're going to say, rather than summing over all derivations, we're going to sum over some subset of derivations that we think in some way will be representative enough. So the obvious thing to do is to have some sort of beam search in the parsing. So let's just, as we're parsing, drop the low probability items and keep going. That will massively sort of prune down the search space by some beam parameter, depending on how aggressive we are. And we'll just use the resulting parse chart as our approximation for Z. One problem with that is that you get a bias doing this. If you try and estimate a function by just looking at its maximum, it's not terribly informative. If you have a function, think of a curve on a graph, what you really want is a few points spread around on the graph that give you an idea about that curve. So maybe a better idea would be to instead sample in some way for this term Z that we need to calculate. So a second idea is to say, well, we can exactly produce a chart without a language model, so let's produce that. Let's sample some of those derivations and use those as our approximation for Z. So this is the second idea, to use sampling from a simpler model. So I'll illustrate that briefly here. So if we have, again, a parallel sentence here, this tree here is its derivation. This is just in a very simplified grammar. This is not what we're actually using, but if we imagine just a left-branching grammar like this. Here is the hypergraph produced by that. So this is a parse chart, essentially, if you follow all these links through.
There is only one tree on the side just to make the picture simple. It should be a forest on the left.
No, this is one sample. So this is one sample is one tree. So what we'll do is we'll take a second sample, and we take this derivation and add it to the first one to produce a chart. So we're actually combining them now into one chart. And the reason we do this is because as we combine two derivations, the chart now represents those two samples we've added plus additional samples that we never added. And as we do this, we'll get essentially an explosion in the number of translations we're actually representing in our chart. And so you can see that here's a translation that we never inserted into this chart, but we can derive from it. So with a linear number of samples, we can produce a massive space of possible translations. And this is essentially a heuristic, so we have no guarantees, but we hope that this will be a better approximation than using the beam as a heuristic. Okay, so more complications. There's lots of complications in this model. So the next complication is how do we deal with the prior? So if you're familiar with log linear models, we always use a prior, and generally it's a Gaussian term is the most popular prior. So we do something a little bit tricky in this model is we're first training a model without the language model, and we do that with a normal Gaussian prior. When we come to train the model with the language model, because we are approximating, we know that we don't want to trust the model too much. So what we do is we set the mean of our Gaussian for the second model to be the result of training the first model. So we say that we've trained a model, we think it's quite good, we train the model with the language model, and we say don't deviate too much from the first model. And that's what we do with a slightly tricky prior here. So what we're doing is, here is the feature weights, and we take the difference with the feature weights of the model without the language model. And so don't worry about too much if you don't understand that, but the general intuition is that we're trying to, because our second model is an approximation, we want a way of constraining it. We want to say don't divert too much from what we think is a good solution, because otherwise the approximation may lead us into a crazy solution. So eventually we end up with something that looks like this. So L is our objective function, and this is what we're optimizing. And we do this using relatively standard techniques, using dynamic programming. The inside-outside algorithm is how we get expectations, which we then use in a convex optimizer. So this function is non-convex. So we've produced a non-convex optimization problem, but we optimize it using a convex optimizer. So we have no guarantees of finding an optimal solution, just hopefully a good solution, dependent on initialization. So some experiments. We experimented with this on the IWSLT data. It's about 40,000 sentences. And we used this stated here, development testing data. One thing to note about this data is that there's a great number of references. So the test data, there's 16 references. And that will, I think I'll comment on that later. It affects the evaluation. And finally, for the first simple model, I'm training with a single binary feature for every rule. So we're learning a different weight for every rule, a word penalty feature, and a feature for the language model. And that amounts to about 3 million features. So in terms of features, you could think of this as much simpler than an existing translation model, but the freedom of the features is quite high because we're learning a separate weight for each rule. Okay, and we're evaluating with the blue translation metric, this n-gram match translation metric. So here's a first table of results. The top line here is the model trained without the language model. This is the model we can train exactly. And that gets a blue score of 32 there. The bottom two are our two approximation models. So plus LM here means trained with the language model. This one here is the one using the beam heuristic, and this one's using our sampling heuristic. And we can see that they both do a lot better than not using a language model. So you need to use a language model. It's a common sort of theme of machine translation, is that if you want good results, you need a language model. It really does matter. Between the two models, we can see there's only a slight difference, but our sampling scheme does do a little better. And we did see this quite consistently. Yes, and the other advantage of the sampling approach is that it produced much smaller charts, so it was more computationally efficient. So this is the one we use in all the subsequent experiments. If we then go on and compare this on, so that was on a development set. Now let's look at the test set and compare against what people currently do in machine translation, the MERT optimizer. So again, we have the model without the language model. Again, we see a big improvement with the model with the language model. The two models between our model and the MERT model are very similar in terms of results. This is on blue with multiple references. I have an extra column here to show the blue score for a single reference, and that's because our model's only trained with a single reference. It has no concept of multiple references, whereas the MERT model is trained with multiple references. So we also see how it does when we just have the first reference, which is more what the model was trained to optimize. And we can see there it does quite well. So we're not getting amazing results, but we're getting in the ballpark of an existing translation model. And in some ways, this is the first sort of large-scale discriminative model to do that. And the other thing to remember is our features are extremely simple. These single binary features on each rule. So that's quite encouraging. This means that our training regime is working, in a sense. We are actually learning a translation model. So that was a very simple model. So let's make it more complicated now and say, well, the whole idea of this was that we argued we can use interesting features that existing translation models can't. So we need to do that now. So I'm just going to present one example, and that's where we use source syntax as a feature. So as I said, the source sentence is conditioning context. So we can have any features from it we like. So what we do is we pass the source sentence, and then we take features from that to inform the translation process. And so now we have a lot more features. We get up to about 7 million features now. And this is, in some ways, is a nice way of getting syntax into a translation model, because it avoids the problems that come when you put syntax into the grammar. When you do that, decoding becomes very complex and slow. By putting it into the source side and using a conditioning context, we don't have any of the computational slowdown. We also don't constrain the model. So we don't say that the model can only produce translation units which correspond to the syntax. It can produce any translation units that it would normally, but when they do correspond to the syntax, we can extract extra additional features which inform the process. So here's what this looks like. We have a Chinese source sentence. We've parsed it, and I've horribly anglicized the parse tree to make it more understandable to myself. And then we have an English sentence on the output. And we're going to use features from this parse tree to inform the translation process. So we're using a high-row grammar, and the example here is a single derivation where we've used 2 steps. The first step is we translate currency exchange office as a phrase, and then we have a gapping translation rule here. The second step, which takes the question, where is the X, and then puts a question mark on the end. So it's a simple derivation where we've translated this sentence as 2 steps. And so what we're going to do is inform this. It's very dark. Read that. By saying in this first step, when we translate the phrase currency exchange office, we're going to notice that that corresponds to this noun phrase in the source tree. And so we're going to have this feature. We're going to say when we see the Chinese, it's a noun phrase, translate it like this. That's going to be a feature, and then we can learn a weight on whether that's a good idea or a bad idea. In this case, we'd hope to learn a positive weight. For the second step, the derivation corresponds to this syntactic unit. So now we learn that when we see a unit like this, here we've simplified the internals of the tree. We're seeing a noun phrase followed by the Chinese and the question mark. The question mark should be on a separate arrow there, I think. Then we produce this English here. So here we're getting information from the syntax tree. We can have it inform the reordering and the lexical choice, but we're not constraining the translation in any way. If the translation rules didn't correspond to syntactic units, these features just wouldn't be present. They're just binary 1 or 0 features. They're either present or they're not present. So we don't constrain anything. So if we throw that into our translation model, and learn it, we see that we improve a little bit more. So we're doing a bit better again. And all these gains are quite small and quite modest. But in many ways they're very encouraging because there's been lots of these discriminative models that have failed to learn much at all. So the simple fact that we can add features and we can get a better result is really quite encouraging. So finally, to summarize this section of the talk, so presented a latent variable conditional model for synchronous grammar translation, demonstrated that it does work. We can learn this model without relying on other translation models to inform it, and we can match or slightly improve on current state-of-the-art models. So that's all very good. The bad parts are this is very heavy, and hence why we're using small corpora. To do this on big translation corpora, you're going to need a very big cluster. Thankfully, it does distribute very well. So if you have a big cluster, you can do it. But it's a very heavy model. And the second bit is that there's something unsatisfying about these heuristic approximations of the Z function that I'm using. And one really interesting future area of research for people to tackle is how can we approximate these spaces in some sort of bounded way? Can we come up with guarantees on these approximations rather than just using heuristics? Okay, so concluding remarks, where I probably say what I just said, yes. So, as I was saying, really interesting questions is how can we come up with much more rigorous ways of doing these approximations? The second one, which I haven't really got at, but is another interesting point from this, is from particularly the alignment model in the first half of the talk, it relied on these hand-annotated examples. So we had this advantage that we could get very interesting features, but the downside was that we needed hand-annotated examples. For lots of languages, we don't have annotated examples, so we really want to look at, can we use these feature-based models, which essentially correspond to Markov Random Fields, can we train those directly on unsupervised data? And in doing that, we might be able to learn much more interesting generative translation models that do better than the existing Giza framework. Final problem here that I didn't really get at as well in that last translation model example that I've been talking about, there's a question of what is the best objective to train. So we're training our model, but we're not quite sure what the best thing to optimize is. Currently, if you want to compete in the sort of state-of-the-art evaluations, you need to optimize. You need to use MERT or something like that to optimize the blue score, because that's what you're evaluated on. So there's a question of what's the best metric to optimize for based on what you're being evaluated on, or secondly, translation quality, because the two aren't necessarily correlated. And certain metrics are more easy to optimize than others. So another interesting bit of research, and some people have looked at this subsequent to my work, is how to optimize other metrics besides likelihood, which is what I used. Okay, thank you. That's the end of the talk. There's some references there.
Any other questions? For example, perceptron, which is another way, algorithm to deal with.
Andre, I think they're trying to give you the microphone.
I wonder if one trains, say, perceptron, which is another way to handle millions of features in your model, one needs to reach the target side translation. Do you have the same issue here, and
Yeah.
how do you deal with that?
Yeah, we need to be able to. We need a derivation of the gold sentence in order to train anything. Otherwise, there's nothing to train. That's part of the problem with scalability as well. What we do is we use a very permissive rule extraction so that about 90% of the sentences are reachable. But that's because we take a very permissive view of what we extract as a translation unit. So we get some very big ones, which are not very good translation units, but they do mean that we can reach a lot of the sentences. This feeds into the other question of which metric we should optimize. Because if we weren't optimizing likelihood, if we chose to optimize something like blue score or word error rate, you wouldn't need to match the reference. So you can just look at the difference between what you're producing and what the gold is from a blue score or word overlap metric. So that has some. So that's why it might be nice to optimize those sort of metrics. The downside is they're much harder to optimize. Mathematically, they don't decompose nicely like likelihood. Yeah, so that's the issues with those.
Thank you. And the related question is, are you, like, if in the parallel data that we have, there is always only one translation, but there are many possible translations human translators would produce. So how does this lack of proper target size affect the models or the underlying math? Is that an issue that you have only one?
But it's sort of an issue. I mean, you can. The interesting thing about these models is if you had multiple references, you could train them towards multiple references. That's not a problem from a probabilistic sense. You just have to have them. Of course, we only have multiple references for very small test set corpora, not large parallel corpora. It is an issue in that you're choosing one canonical way of translating, but it's going to be very hard to get around that because that's all the data we have in a sense. Yeah, I'm not sure there's many ways around that. You could, of course, part of the story is regularization, so you can, of course, soften the model and say, don't trust too much what you're learning. So rather than sort of trying to match exactly your reference, just try to get close and leave some ambiguity. So there are sort of ways of you can view that as a smoothing and regularization problem to make sure that you're not overtraining.
And the very last question is, you mentioned that the model is heavy, so how heavy in terms of...
Well, this corpus was quite small, hence why we chose it. I'm trying to remember. It was a while ago. What sort of numbers? I think I was using about 50 CPUs, 55. I think it was taking less than a day, so maybe 20 hours to train one of the models. Yeah,
And to translate is...
translates just as fast as normal translation. So that's one nice property. So it is heavy, but only in the training phase. So if you're a company or something wanting to do this, you can afford to do the training offline. The decoding can still be as fast as normal models. And particularly if you do those syntactic type experiments, it's much faster than using something like ISI's syntactic model. It's fast like IRO is fast or a phrase-based system. So
The parallelization is, you can split the training data and
yeah, it's trivial. So you just distribute the sentences on the different
sum it once.
and machines and sum it back once for each pass through the data.
we don't